Okay, we just finished up with doing line integrals and using Green's theorem. So our next step is to move on to surface integrals, and we will get to Stokes' theorem eventually with that also. So in order to understand line integrals, we had to talk a lot about parameterizing curves, and now we're going to parameterize surfaces. So, and if you remember, when you took Calc BC, and we finished all of the AB material, and then we said, all right, now we're going to move on to polar vectors and parametrics. Okay, and we might have done parametrics first. I can't really remember, but if you remember, x, oops, that's, we'd have x as some function of t, y is some function of, not the same function, some function of t, and t would be between a couple values. Okay, and that was our parametric equation for some curve. Okay, and then we said, well, let's do the vector equation. And the vector equation was just the parametric equations with the I and the j on them. Remember that? Where we would say, okay, it's f of t in the I direction, g of t in the j direction. There's your vector valued function. Okay, and we kind of talked about how it's very easy to just kind of swap between these two. Okay, and that's what we'll do in 3D as well. All right, so we'll have, let me just kind of get a different color going here. So we'll have some vector, but we'll have two parameters, right? Okay, 3D, we're going to bump everything up by a dimension. Okay, so we're going to have parameters u and v. So x would be a function of u and v, just a slightly different notation here. Okay, in the I direction. Y is a function of u and v in the j direction. And then we'd have z is a function of u and v in the k direction. Okay, and your parametrics, x is x of uv, y is y of uv, and z of uv. And that would get you a point in space. Okay, so if you look at an example, this is exercise 4 in your book. Are the parameters they use for this one are s and t, right? We have this in component form. S times the sine of 2t. Maybe they shouldn't have chosen s, knowing that we're going to have sine. S squared and s cosine t. I'm sorry, 2t. Okay. So much what we've been doing in a lot of the things we've done in class is thinking about in what's happening in different planes and in different directions. Okay. The obvious pairing here is in your xz plane. Okay, where x is s times the sine of 2t, and z is s times the cosine of 2t. That's just a circle with radius s. It's almost like your parametric equations for your unit circle, right? In your unit circle, x is 1 cosine theta, z is 1 sine theta. The fact that it's 2t just tells you how quickly you're moving around the circle when you parameterize it. When t actually means something like time, it tells you how quickly you're moving around the circle. But it's just a circle with a radius s in the xz plane, okay? And then you can see, too, that in your other planes, like in your xy plane, x is s times the sine of 2t. Y is not dependent on t at all. Okay, so whatever, that sine of 2t would be constant for some value of t, y is just s squared. It's going to be a parabola in your xy plane, where as s increases, y increases by s squared, right? Okay, and again, that 2t, that's like your stretch factor of a parabola, that sine of 2t. Okay, so what we would have there, and you have something similar too then with your yz plane. Okay, so just kind of thinking through those things, and then you can kind of sketch it. This one would be a circular paraboloid. Again, in your xz plane, we'd have circles. Okay, and let's see, kind of, okay, as S gets bigger, and you can kind of see the parabola shape that we would have in like your XY plane or your YZ plane. Okay, and that's your general idea. That's a circular paraboloid with the y-axis as its axis. Okay. Another example that's in your book that you might, the one that we just did is, I don't know, I think it's a little hard to think through when you think about your two parameters. You kind of have to think about what happens when like you hold one of them constant. In this case, t was the one that made sense to hold constant. T just kind of tells you where you are along this circle. S is the one that gives you like more information, how far you are up and down that y-axis. Okay. But anyways, here's another example. This is exercise 16 in your book, I believe. We want the parametric equations for the plane through the point 0, -1, 5, okay, that contains vectors 2, 1, 4 and -3, 2, 5. Okay, and it's not as difficult as it kind of seems. It's actually really straightforward. I think example 3 in your book kind of walks you through. Call this P naught. If P naught is at 0, -1, 5, and that's also, that can be a position vector. Okay, to get you there. Then let's call this one. I'm not even gonna call it. Let's say that this vector in 3D space is 2, 1, 4. Okay, and then this vector in 3D space is -3, 2, 5. Okay, so we're containing those two vectors, and that brings us to the point, again, this is P naught, the point XYZ. Okay, and again, those vectors, remember, those just give you a direction. So any scalar multiple that would take us, A units in that direction and B units in that direction will get us to any point on the plane. It's analogous to just your Cartesian coordinate system, right? Any ordered pair tells you how far you move in the x direction and the y direction. Now we're just moving in the 2, 1, 4 direction and the -3, 2, 5 direction. And even that might overcomplicate things, because basically all you're doing is 0, -1, 5, plus, I'm going to use, instead of A and B, I'm going to use U and V, just because U and V are kind of more, I can use param. What do I want to do? I can use parameters A and B. We'll do that. A times 2, 1, 4 plus B times -3, 2, 5 gets me to XYZ. Okay, and I'm just points, the initial point and the terminal point, I'm just saying is a vector function to get the location there. So X would equal 0 plus 2A minus 3B. Okay, Y would equal -1 plus A plus 2B, and Z would equal 5 plus 4A plus 5B. Is that straightforward? That's your parametric equations for that plane. Okay. If A and B are 0, you're at your point. If A and B are not 0, you're at least moving in those directions to get to another point, which means, if we're moving in these directions, our plane contains those vectors. Okay, and that's it. Okay, we got another one. This one is exercise, I think, 20 in your book. It uses some spherical coordinates. We want the parametric equations for the sphere, the portion of the sphere, x squared plus y squared plus z squared equals 16, between z equals -2 and z equals +2. Okay, so it's kind of like a ring shape, right? We'd have this sphere with a radius of 4. I'm going to bring those out a little bit more. Not much more. A little bit more. 4, 4. Okay, so this is like the equator of your sphere. Ooh, that was kind of messy. Top of the sphere, bottom of the sphere, but only between z equals 2 and z equals -2. So we'd have kind of like this ring, and, well, this ring. It'd be a shape, kind of looks like that. Okay. So spherical coordinates, obviously, right? Makes the most sense. So x equals r, which is 4, or sorry, I should say rho, sine phi cosine theta. And that's just how, that's your spherical coordinates, right? Y is rho sine phi sine theta. Okay, and then z would be 4 cosine phi. Okay, well, how do you get only that portion of the sphere? You limit your parameters, right? Your parametric equations, going back to, what we wrote up here, you gotta know what your parameters are between. Okay, so obviously, theta is between 0 and 2 pi. Okay, and then our other parameter that we're using is phi. Okay, right, rho is constant. Rho is just 4. Okay, so there's only 2 parameters that we have going on here. So phi, we got to think a little bit about that. Okay, again, we're going to this point here, okay, which would give us a 4 here and a 2 here, right? Okay, which gives us, well, could we do this? There's different ways we could do it. We could do it with trig. We could do it with just the fact that when z is 2, 2 equals 4 cosine phi. Okay, so the cosine phi is 1/2, so phi would be pi over 3. Ooh, I think, do I have this written? No, what has cosine of 1/2 would be pi over 3. Hold on a second. Yeah, this is right. So pi over 3. And by symmetry, we'd have to go, if this is pi over 3, then we'd have to go to 2 pi over 3 because of symmetry. Okay. There's other ways that we could do it. Remember, we were finding phi there. If you want to do right triangle trigonometry, if this is 4 and this is 2, the sine of alpha would be 2 over 4. Okay, so sine is 1/2 if alpha is pi over 6. If this is pi over 6, then this one has to be pi over 3. Okay, so we could get that way also. All right, but here's your parametric equation, and here are the bounds on your 2 parameters. Okay. Next thing we're going to talk about, surfaces of revolution. So remember when we did revolutions in calculus, you guys liked that so much. Okay, so, and I don't even think they really give you too many examples on this one, but if we have y equals some function of x, wherein and f of x is greater than 0, so we're equal to, we're at least above the x-axis, and x is between a and b. Okay, and then we rotate it around the x-axis. Okay, so we've done this before, right? We never really thought about it in 3D terms. From A to B, okay, we'd have our f of x. Okay, and if we rotate it around the x-axis, remember, you would think about that coming out of your screen as the z-axis, right? Okay, so in 3D, x is x. Okay, theta is your angle of rotation. So the way I've drawn it now, theta is 0. We have not rotated it at all, okay? Then as we rotate it, we make circles, right? And your parametric equations of the circle is r cosine theta and r sine theta, okay? So your radius of the circle is whatever f of x is, and then cosine theta, and z would be your radius times sine theta. Okay, so you can think about it. If theta is 0, if we haven't rotated at all, then y is f of x and z is 0, right? We're flat in this xy plane, okay? If we've rotated it maybe pi over 2, okay, then y would be 0 and z would be f of x. We think about, this curve rotating basically 90 degrees out of your screen, okay? And eventually what's going to happen is, if I can draw this somewhat well, we have x and y, right? The way I have it drawn now from A to B is it kind of goes up a little bit like that, okay? That would be when theta is 0. When theta is pi over 2, I'd be kind of up here in your xz plane, okay? And eventually I'd rotate it all the way around. This piece here is meant to be in the xz plane. This piece here is in the xy plane, okay? And if I rotate it eventually all the way around, I'll eventually have something that looks like, this is that, okay? Whatever, and theta goes around the circular, oops, that should be right down the middle. Theta is around here, okay? This is your x, your y, and your z, okay? So that's how your surfaces of revolution work in these parametric equations and these 3D equations, okay? We'll probably revisit this in class as examples come up because I don't think there's a whole lot of it in the homework. The next thing we're going to talk about is tangent planes, which we talked about a little bit too, right? But when we have those surfaces, okay, so we have a surface such as, again, let's get that vector equation for the surface. Okay. And we're going to take the partial derivatives. So our u is going to just tell me the behavior in the u parameter of x, y, and z. Okay, as u changes, the changes that I could expect to see in x, y, and z. So dx, du, dy, du, and dz, du. Okay, and then you can probably guess we could take our partial in v, which would describe how v changes as v changes how x, y, and z change. So dx, dv, dy, dv, and dz, dv. Okay, almost like a gradient, right? Okay, where it tells you how we're changing in those parameters. Okay. A couple of things that your book points out: if the cross product of these two vectors is not 0, then the surface is smooth. There's no 90-degree angles between them. Okay, the surface is smooth. No corners. Okay, also points out that your tangent plane contains these two vectors. Okay, it's kind of like how a tangent line is the derivative, right? Your tangent plane has both of these partial derivatives. Okay, or I should say your tangent line has a slope that's the derivative. Okay, just like we've learned before, the cross product of two vectors is the normal vector in the tangent plane. or to the tangent plane. Okay. And then remember your vector equations. The normal vector, the normal vector is ABC, and point x naught, y naught, z naught. Then the tangent plane is A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. Okay, and that's from chapter 10, but this equation is going to come up again. Okay. All right. So if we look at exercise 30, they give you that x is u squared plus 1, y is v cubed plus 1, and z is u plus v. And we have a point on this surface, 5, 2, 3. Okay. Which tells us if that point is on the surface, let's see, u would have to be 2 to get that x value, right? V would have to equal 1, and then the z checks out. Okay. This could also be written as a vector. Just like we were saying before, parametric equations can be vector equations very easily. Okay, but we're supposed to find the equation of the tangent plane at that point. Okay, so at that point, first of all, the partial with respect to u would be 2u, 0, 1. Okay, so are you going to the store? Are you 2, 1 would equal, excuse me. All right, I don't need that yet. Sorry. I don't need that yet. Okay. And then our v, right, would equal 0, 3v squared, 1. Okay. So there's these guys here. Now we want to find the normal vector by doing the cross product there. Okay. So cross ijk, 2u, 0, 1, 0, 3v squared, 1. Okay, and I'm going to have, let's see here, in the I direction, I'll have 0 minus 3v squared. In the j direction, I'll have negative 2u. And in the k direction, I'll have 6uv squared. Okay, so there's my normal vector. Okay, so the normal vector at that point, when u is 2 and v is 1, would be negative 3, negative 4, and then 6 times 2 times 1, so 12. Okay, so the tangent plane then, so the answer, okay, would be A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught, equals 0. We're going to expand that out. So I'll have a negative 3x plus 15, okay, minus 4y plus 8, plus 12z minus 36. I'm just moving those constants to the other side right away. So negative 3x minus 4y plus 12z is negative 23 plus 36, so that is 13. All righty. Okay. The last thing we're going to talk about is surface area. There's kind of a lot going on in this section, a lot of little things. Okay. So for surface area, and again, we're going to think about that vector equation for the surface. And I'm actually just going to leave it in component form because I'm sick of writing linear combination form. We've written it enough times, right? Okay. And U and V are within this domain. Okay, so XY pairs that are within D. Okay. And as long as S is covered once, is UV ranges throughout D. Okay, so S is covered, covered, is it gonna work? Covered once is UV, once, come on. Okay, as UV ranges through D. Okay. So basically the surface can't double back on itself. It's, you know, it's one surface above that plane. Okay. Your surface area. I'm going to give you the equation first and then show you why it works. Your surface area, which your book uses the notation A of S, is the double integral over D of the cross product of U, those partial U and V's, dA. Okay, where that D is in your XY plane, okay, and then the surface is described by R. Okay, so it almost gets back to, remember, you think about your base in the XY plane, your height in the Z direction. Okay, why does it work? Because we want to think about, remember, R of U is like your slope in the U direction. Okay, it tells you how X, Y, and Z are going to change as U changes. So it's like your slope of U, okay, or slope in U, I guess. I'm going to do in U. R of V is like your slope in V. Okay, so if we have like this curved surface, you know, and we've got this specific point here, then we can say, well, here's the direction, right? These are directions R of U, but times delta U, okay? And then R of V times delta V. We're going to get some changes there, okay? These vectors will show how much these vectors should be moving in the X, Y, and Z direction, okay? And then if you remember, the cross product of a vector gives you the area of a parallelogram. Okay, so we're kind of thinking about like these infinite parallelograms, and they're giving us this nice area. Okay, and that these guys can kind of be incorporated into the dA. Okay, it might be kind of a little bit of an oversimplification here, but again, it kind of gets the fact that that cross product is going to give us an area of a parallelogram, and these are going to give us the sides of the parallelogram. Okay, and together that's going to give us a surface area. Okay, so an example for this one, and I think this is exercise 34 in your book, R is U plus V, 2 minus 3U, 1 plus U minus V, with U between 0 and 2, and V between -1 and 1. We want to find the surface area. Okay, so the surface area of this surface, okay, is U and V or in this rectangle where u is between 0 actually square, u is between 0 and 2, and v is between -1 and 1. Okay? So remember, we're going to do the cross product of RU and RV. So we got to find RU, oops, which would be, that should be a U. Okay. 1, -3, 1. And then RV is 1, 0, -1. Okay, so our cross product, we're going to do IJK, 1, -3, 1, 1, 0, -1. Okay, so we'll have 3. And we'll have -1 minus 1 to get -2, but then we make it positive. And then for K, 0 minus -3, so 3. Okay, and we wanted the magnitude of that, right? The magnitude of that cross product, that's what those bars mean. Okay, so the magnitude of that cross product is going to be 3 squared plus 2 squared plus 3 squared square root, so the square root of 22. Okay, and then we are going to, we have to think about your integral from -1 to 1, the integral from 0 to 2, the square root of 22, du dv. Okay, which you can do, go ahead, but remember, this is just a square. Okay, so if I take out that square root of 22, I'm just finding the area of that square. Okay, so it's the square root of 22 times 4. And that's my final answer. I could go ahead and do the integral if I wanted to, but remember, the integral of 1 is just finding the area, right? And we're between 0 and 2 and -1 and 1. That's just a square. That's 2. And if you go from 0 to 2, that's 2. Okay, it's a little shortcut there. All right. So that's pretty straightforward if it's in vector form like that. The other surface area that we want to talk about is if it's more in function form. Okay, surface area of a function. I should say graph of a function. Okay, so when z is some function of x and y, and that gets you your surface. Okay, so for that one, the area of the surface, and you've seen something similar. So when you did surface area of parametrics, okay, if you remember, actually surface area and just function, remember you had 1 plus f prime of x squared. Okay, so here, let me do, when you did functions, you did the integral of the square root of 1 plus dy dx squared dx, and that was from a to b. And then when you did parametric, you did integral from a to b the square root of dy dt squared plus dx dt squared dt, and a and b were t values. Remember that from Calc BC? Okay, so we're going to do something really similar. Okay, we're going to have 1, which is technically the partial of z with respect to z, plus the partial of z with respect to x squared, plus the partial of z with respect to y squared. And then that will be a dA. Okay, so it's kind of the next step. Okay, and we talked about too how that 1 is technically dx dx. Okay, your parameter when it's in function form is just x. Okay, so you take your derivatives with respect to your parameters, then you switch to parametric, the parameter was t, okay, and now we're looking at your surface area here where basically your parameters are x and y. Okay, all right, so again, you can think of that 1 as being if we had dz dz there. Okay, but that's just 1, so we don't need it. All right. And D is in the xy plane. Okay, so that dA is going to be dx's and dy's. Okay, that will be dx, dy, or dy, dx. Okay. All right, so we'll do a couple examples of this, and then we're going to be done. All right. So our first example, this is exercise 35. We want the surface area of the plane, x plus 2y plus 3z equals 1. Inside the cylinder, x squared plus y squared equals 3. Okay, so we're thinking about that cylinder with a radius of square root of 3. Okay, and then this plane comes slicing through it. Okay, so you can kind of think, let's see, it slices through where z is 1/3, and x and y are 0. Okay, where x is 1, it's not to scale, and where y would be like 1/2. So we just kind of have this, we're slicing through it. Okay, so I'm just going to do like after we have sliced. Okay, there's your cylinder. And these points are on this slice, basically. Okay, we want the surface area of that slice. So we're looking for the surface area of that plane as it slices through the cone. Okay, I hope it makes sense. Okay, the same 3 points that I drew on here would be kind of in the middle, just on that surface. Okay. All right, so the first thing that we need to figure out is dz dx. Okay, which means we need to solve that guy for z, right? So we would have z equal 1 minus x minus 2y over 3. Okay, so the derivative of that with respect to x would just be, I'm looking at that negative 1/3. And the derivative of that with respect to y, I'd be looking at that negative 2/3. Okay. D is in that xy plane. Okay, so if I just am thinking about this cylinder, it's that circle in the xy plane. Okay, it is, if I were to take that surface and just squish it to the xy plane, the area that's being taken up by it. Okay, so in the xy plane, maybe polar would be better for this one, where r would be between 0 and square root of 3, and theta would be between 0 and 2 pi. Okay, so rather than doing my rectangular coordinates that I might do, when I sit up here, that could be in terms of x and y, I'm going to switch to polar. Okay, so I'd have the integral from 0 to square root of 3, integral from 0 to 2 pi, square root 1 plus negative 1/3 squared plus negative 2/3 squared. If I am switching to polar, I need that r dr d theta. Okay, so underneath that radical, I'm going to have, I already figured it out ahead of time, it's the square root of 14 over 9. Okay, so that's the square root of 14 over 9, which would be square root of 14 all over 3. Okay, so I could integrate that. Okay, and I can go through and do that. I can also kind of cheat like I did in the last one, right? I know that that is a circle with a radius of the square root of 3. Okay, so D is a circle with radius, square root of 3. Okay, so the area of D is just pi times r squared, so 3 pi. So I don't even need to go through and do that integral. I know it's going to give me 3 pi. Okay, so I can just do square root of 14 over 3 times 3 pi. So square root of 14 pi. Okay. We'll do one more. Okay. The next one, the last one here, it's exercise 36, I believe, in your book. Okay. We want the surface area of the cone z equals the square root of x squared plus y squared. So remember, that's your cone with that 1-to-1 ratio. The z direction as you go out 1, up 1. Okay. Between the plane y equals x and y equals x, and cylinder, sorry, y equals x squared. Okay. So, and remember, z will always be positive because the square root. So we're looking at the upper nap of the cone is what they kind of call it. So in your xy plane, we're looking at y equals x and y equals x squared. Which we know intersect at 0, 0 and 1, 1. Okay, so this is kind of a weird thing going on here. In 3D, if I try to draw it, we're looking at, there's your x equals y, and your x equals y squared, or sorry, it's y equals x squared. Okay, and then we've got a cone. Okay, so if you kind of think about it, we only want the pieces of this cone that are above that. Okay, so we're kind of like, it's very strange and not super easy to draw. Kind of like that. Eventually we're going to have it line up. Okay, that's weird. It's hard to draw. Okay. But anyways, we can go ahead and go through our process, right? dz dx. So that'd be 1/2 x squared plus 1, x squared plus y squared to the negative 1/2 times 2x. So the 2's cancel out, and we'll have x over the square root of x squared plus y squared. Okay, and we're going to get similar for dz dy, right? Because x and y are just treated the same in this equation. So dz dy would be y over the square root of x squared plus y squared. Okay, and then our region D here, x is between 0 and 1, and y is between x squared and x. Yes, for some reason I have it different in my notes, and I think that's a mistake. I hope. Let's see, x is between 0 and 1. Y, the lower bound is x squared. Oh, I do have it the right way in my notes. Okay, let's double check in my notes there. Okay, so I want the integral from 0 to 1, x squared to x, the square root 1 plus x over the square root of x squared plus y squared squared plus y over the square root of x squared plus y squared squared. Okay, and then I've got dy dx. Okay. Now, what happens here is actually kind of good. We have 1 plus x squared over x squared plus y squared over x squared plus y squared. So we can change this to x squared plus y squared over x squared plus y squared. Don't forget, we're going to do the square root. So what we end up here is the square root of 2x squared plus 2y squared over x squared plus y squared, which is the square root of 2x squared plus y squared over x squared plus y squared. That's just 1. We end up with the square root of 2. It looked like it was going to be a huge mess, and it's not. It's really easy, okay? And in fact, we're going to take that constant out of there and then do my nice integral here. This is kind of fun. I like it. Okay, so I'm going to do that integral. Nope, getting a little glitchy here. So this would be y evaluated from y equals x squared to y equals x. So that would be x minus x squared. Okay, so I'll have the square root of 2, integral from 0 to 1 of x minus x squared dx. So square root of 2, x squared over 2 minus x cubed over 3, evaluated from x equals 0 to x equals 1. 0 is not going to get me anything, the 1 is. So I have the square root of 2 times 1/2 minus 1/3, which is 3/6 minus 2/6, okay, which is 1/6. So square root of 2 over 6 will be my final answer there. Okay, and that is it. I think we touched on everything. Let me know if there's anything that you need some help with, and we'll do more in class.